Welcome. Let me say something about the curvature landscape, something I have worked on the last 15 years, and it's a very interesting story. So curvature is something you can attach to a geometric object, and there are different ways to deal with geometric objects. We can either focus on clarity and then look at graphs, or we can look at simplicity, which is simplicity complex as just one axiom, or we can look at generality. Delta sets are kind of the ultimate way we can produce products and subspaces, open sets. A lot of constructions which are not possible here are possible here, but the idea is the same. We have a finite set always, and we have simplices, so objects of various dimensions, and then there is an energy which is attached to each of these objects. The most natural thing is that you have just omega x, which is just -1 to the dimension of x attached, and then you get the Euler characteristic. So you can define Euler characteristic in each of these cases, and if you take these energies and you push it to the zero-dimensional part, you can do that in every case. Here, if there is a zero-dimensional part, if there is no zero-dimensional part, you just push it to the lowest dimensional part which exists, and then you get a curvature located on these low-dimensional parts, which are usually vertices. And so this has a long history. So maybe the first time that in the discrete or the finite curvature has appeared is Eberhard. And Eberhard was a blind mathematician, blind geometer, and he has this formula which is then has turned out to be very important in graph coloring. So if you have a two-manifold, it's just for two manifolds, two-dimensional manifolds, triangulated spaces like this, and you just look how many neighbors there are. If there are 6, then there is zero curvature. So in this case, this is actually almost zero curvature. So all the curvature is located here on kind of a few points. But it's an interesting notion. It's a little bit rigid. You know, you can, for positive curvature, you can only have, 5 neighbors or 4 neighbors if you want to have a manifold. And then in the one-dimensional case, this is also well known. It's 1 minus the degree, for example, for trees or cacti, or one-dimensional graphs which have no kind of higher dimensional structure attached, so no triangles, triangle-free graphs. So, for example, give you this beautiful curvature, and this generalizes then to arbitrary networks or arbitrary simplicity complexes. That's this Leavitt curvature, is just pushing everything down to the zero-dimensional part. So I discovered this myself in 2011. It turned out in the 1992 that Leavitt has already looked at that. He didn't look at it as a Gauss-Bonnet result. I actually looked at it as a Gauss-Bonnet Chern result because it's a higher dimensional version of Gauss-Bonnet, and especially for manifolds, for example, for 4 manifolds, I wrote down just dimension by dimension for manifolds what the curvature is until I kind of then saw this. This actually is using some Dane Somerville relations also, and I saw them experimentally that odd-dimensional manifolds have constant curvature, 0. This is a notion which doesn't even exist in the continuum because you don't look at curvature of odd-dimensional manifolds. Gauss-Bonnet Chern is a Pfaffian, so it only works for even-dimensional manifolds, and so I saw that, and I proved that then using Poincare-Hopf. Poincare-Hopf is also another general result. You can see it as a Gauss-Bonnet result where you push the energies just depending on a function, you push it just, to one vertex in the simplex. So if you have a total order given on the simplex, it defines your curvature, which depends on this total order, which depends on the vector field, so to speak. So this is a Poincare-Hopf, which can be seen as a Gauss-Bonnet, but if you average over a probability space of functions, then what you get is you get index expectation, which is much more flexible because you can vary the probability space, you can vary the weights, so to speak. In machine learning language, you can change the weights and you can get different curvatures, and maybe there is some curvature. I was looking for some curvature which in the case of positive curvature manifold would produce positive curvature which satisfies Gauss-Bonnet. The point is that you always want to have Gauss-Bonnet. I'm not interested in curvatures which don't satisfy Gauss-Bonnet exactly. So it has to exactly satisfy Gauss-Bonnet. This is a beautiful curvature which satisfies Gauss-Bonnet. Also, index expectation satisfies that exactly. So here is a nice generalization which I kind of looked at in the context of Dehn-Sommerville. Dehn-Sommerville is a symmetry for this index generating function. If that has a symmetry between -1 and 1, then there's one root, especially at -1/2, then you get Dehn-Sommerville, spaces. Dehn-Sommerville spaces are more general than spheres. So they satisfy the Euler characteristic of spheres, but they are inductively defined without any homotopy or anything. You just want that the unit spheres are one-dimensional lower than Dehn-Sommerville spaces. Very, very elegant, and immediately gives you also that Dehn-Sommerville spaces in odd dimension have zero curvature, and because the curvature can be written as the curvature of spheres using this formula, right? What we have is the curvature is actually cut to the value at t-1, that this relates to the curvatures of the unit spheres. And that's the most beautiful way. That's kind of much more, it's the same. That in this case at t equal to -1 gives you this, but this is much more beautiful. One line of mathematical code can generate you the index generating function for an arbitrary graph, which is very nice. It's not as fast. Of course, this is a NP-complete problem to find complete subgraphs. So, and then I generalized this also. You can, instead of this omega x, which is -1 to the dimension of x, you can just attach to it any ring element, and then you can get the total energy. This is kind of a generalized Euler characteristic. Everything gets more simple, and especially the energy theorem, which I proved in 2016, which is very nice. So in the case when this is equal to omega x, these operators L and the inverse, they are unimodular. They have determinant 1 or -1, which is very, very nice. But this is a kind of more general framework, and in this more general framework you have an energy theorem, unimodularity theorem, you have curvature you can see as a potential energy, and the total energy is the sum of all overall potential energies. That's a nice way to think about curvature. And another generalization is going to multilinear valuations or higher characteristics like the Wu characteristic, where you look at clusters of simplices, and not just at the simplex, but clusters of simplices which intersect, and you can have also an energy theorem. And it's very, very, very nice. You have all the theorems generalize to this multilinear valuation. So not everything here goes over to delta sets. So there are some, like the energy theorem doesn't kind of work for general open sets here, open sets in a simplicial complex. But another version was kind of for Poincare-Hopf was looking at the directed graph. A directed graph which has the property that on every simplex it induces a total order, or you can kind of generalize this and say, I just want to have a total order on every simplex, or I want to have a notion which gives me from a simplex a vertex, the minimum, for example. And then you have a notion of a vector field. A vector field is kind of then Poincare-Hopf for vector fields, and not just, gradient fields like the Poincare-Hopf, the original Poincare-Hopf. So that's kind of a nice thing. And last year I looked at form curvatures. It's the same idea than here. You push everything to the zero-dimensional part, but you can everywhere also, you can push the energies to the, m-dimensional parts, and you get the m curvature, as long as the m-dimensional simplices cover the whole space. So for example, if you take a the two manifold and you take a hair going out, then the triangles don't cover the whole two manifold because the hair is not covered. So in that case, the the Gauss-Bonnet would fail, but you just push everything to the k-dimensional parts, and that's then also was very useful now in the context of sectional curvature when we look at sectional curvature, because what you can do, you can iterate this. So you push everything to the highest dimensional simplices, and then you push everything again to the zero-dimensional simplices. This produces a second order curvature, which I was looking for since 15 years. So I was, for example, looked at here in 2010. I saw that for Fuller-Raynaud or most nice manifolds, you have when you take this curvature here, 2 times the length of the unit circle minus the length of the circle of radius 2, if that exists. It doesn't usually exist, but in nice manifolds exists. Then I saw this formula that it's just 30. I saw that the sum of the curvatures is 30 times the Euler characteristic. For example, for a sphere, I got over 60. For a Fuller-Raynaud, I got over 60. So that was nice. It was a second order curvature, this Puiseux curvature, but it doesn't always work. It doesn't work for general two-dimensional manifolds. And so I kind of abandoned it. But now kind of it comes back. The second order curvature you obtain by pushing everything to the highest dimensional simplices and then pushing it to the zero. That's in the two-dimensional case. This is the Ishida-Higuchi curvature I talked about. Right? Gromov has also looked at that. And so we have this thing, and then you push everything to the zero-dimensional part. And then in the two-dimensional case, you just divide by 3, because you started with a triangulated manifold. This is pretty cool, and it's a curvature which works very well. It has positive curvature for manifolds which you want to have positive curvature. It has negative curvature if you want to have negative curvature, zero curvature if you want to have zero curvature. And maybe it's a good notion for proving theorems, like you want to prove that a simply connected manifold which is a positive curvature, sufficient pinched, is a sphere. So that's a discrete sphere theorem, which is not yet done. It is, of course, trivial in dimension 2, because positive curvature means positive Euler characteristic, which means that it has to be a sphere or a projective plane, but a projective plane is not simply connected. So the sphere theorem in 2 dimensions is clear in the discrete, but you want to have it in 3 dimensions. It's you don't even need positive curvature by the Perelman theorem, and there's obviously should also be a discrete Perelman theorem, and in 4 dimensions, that would be the next thing, prove that if the sectional curvature is positive and sufficiently pinched, then you have a 4 sphere. And this is actually kind of a place where I experiment also, kind of especially with the projective plane, the complex projective plane, which is kind of the interesting case in the continuum where it's 1/4 pinched and not a sphere. And in this case of the discrete projective plane, complex projective plane, also has positive sectional curvature. Okay, that's it for today.